Hypothesis testing. The reality is it's based on samples. There is some uncertainty to your results. Now, you're going to make a decision based on your test. You'll either not reject the null or you'll reject the null. That's your job. The reality is there is some population truth. You might not have the population. You may never know the population truth, but it still exists. So the reality is the null is either true or false. You don't know that. But let's say the null was true and you don't reject the null. Well, great, you've made the right decision. If the null was false and you rejected the null as your test decision, well, again, you've made the right decision. But if the null really is true, but you reject it because you say, well, the sample mean was a bit too unlikely for what we were working on, and that can happen. I mean, you're rejecting because it's, say, the least likely 5% to occur, but it could actually be that that is part of the same distribution. So that would be an error, and in fact we call it a type 1 error. So if you reject the null, there is a type 1 error chance that you've made a mistake, and that's in fact represented by alpha. So if you do a 5% test, there's a 5% chance that you'll reject the null when in fact it is true. What about if the null was false and you didn't reject it? Well, that's what we call a type 2 error, and it has a different probability, beta. You can calculate that, but we're not going to in this course. For our purposes, it's fine just to think about alpha. Now, in terms of type 1 and type 2, why do we give them different names? Well, they're different errors. Null being true is like the person being innocent. Null being false is like the person really being guilty. So the idea is a type 1 error is like sending an innocent person to jail, and a type 2 error is like letting a guilty person go free. So they're different errors, and in real life what you can do is you can think about which of these you want to minimise, and of course we can measure them. But from our perspective, I just want to make sure that you have an awareness that when you come up with your conclusion for a hypothesis test, there's still a chance that you're wrong. So you need to know what the chances of making that type of error are. Okay, and I've got that, of course, in the slides as well. Now, this does link to confidence intervals. So the reality is that if I had taken the same TV data and worked out a 95% confidence interval, remembering I did a 5% hypothesis test, if I had worked out a 95% confidence interval, my range would have been from 2.68 to 2.9968. So I'm pretty much saying that there is a 95% chance that the true population mean is within that range. Does that range include 3? No, it doesn't. So it corresponds to the same conclusion that we came up with from our hypothesis test. So for a two-tailed hypothesis test, it does correspond to the confidence interval result. So I just wanted to give you that as a reference to show that, you know, all these topics are tied together. Now, of course, we're focused on a two-tailed test, but we could have just as easily wanted to focus on a directional test, a one-tailed test. And so we'll have a look at an example of one of these. It does depend what direction you're going in. The idea is if your alternative is that the mean is, say, above 3, well then your rejection area will be in the upper tail, whereas if your alternative is that the mean is less than some value, then your reject region will be in the lower tail. So we've got a phone industry manager claiming that customer monthly cell phone bills have increased and now average over $52 a month. We want to test at an alpha of 10%, and again we're going to assume that sigma is known and it's 10. Now our change, we're looking to see if the mean is now more than 52. That becomes our alternative hypothesis, and we can work backwards to the null, remembering that they're complements of each other. Okay, so we set up our decision diagram. It's a one-tailed test. We're only going to reject the null if we get a sample mean that's sufficiently high, so only in that upper tail. 10% level of significance, the upper tail includes that entire 10%. Use your inverse table, the cutoff is 1.28, so we've got one reject region and then everything else is do not reject. You take a sample, let's say the sample mean is 53.1. So the average bill is $53.10, and that was based on a sample of 64. Now what you're really asking yourself is a sample mean of 53.1 sufficiently above 52 for you to reject the null? Or is this still just a number that you might get as part of natural sampling variation, even if the true mean was 52? Well, turn it into a Z-score. It comes out at 0.88. Where does that lie in terms of the sampling distribution? It's clearly in the do not reject region. So what this is saying is that $53.10 is not far enough above $52 for us to reject the true population mean of being 52. Instead, we don't reject, we say there's not enough evidence. So that's really just code to say, well, $53.10, that's the kind of thing that we could get just because of natural sampling variation. So again, write your conclusion in terms of the null, then in terms of the alternative. So it's that very repetitive step-by-step process, starting with the null and the alternative, ending with the conclusion. We could have just as easily used a p-value. Now when it's a one-tail test, your p-value is based on getting your test statistic and just the area then created in that one tail, so you don't do the multiply by 2. So the odds of getting a z-value greater or equal to 0.88 comes out at nearly 19%, clearly well above our alpha, so therefore same decision as before, do not reject. So it didn't matter which technique we used, we still get exactly the same result. What do we do if we're working on means and sigma is unknown? Well, no surprise, all we're going to do is use S instead of sigma and use the T distribution. So we've got a claim that the average cost of a hotel room in New York is $168. We take a sample of 25 hotels. Our sample mean is $172.50. Sample standard deviation $15.40. We want to test the claim at 5%. There's no reference in this question to testing to see if it's above 168 or below. We're just looking to see if it's different. So it's an equals not equals two-tail test. Is $172.50 far enough away from 168 to reject the null, or is it close enough that it's just part of the sampling process? Set up the distribution, this time using T. So if it's a 5% test, still 2.5% in either tail because it was two-tail. Use your T distribution, degrees of freedom 24, just n-1. Set up those two boundary points. Change your sample mean of 172.50 into a T value, and once again compare to see where that lies. It is clearly in the do not reject region, so it's saying that we can't reject the null. $172.50 is still close enough to 168 that it's likely to have occurred with the null being true. So every time you do these, try and remind yourself, even though you've got your formal conclusion, remind yourself of what this is really saying. And again, you could work out a confidence interval. You would find that there is, say, the 95% chance that the true mean is between 166 and 178. That includes that 168 that was our null hypothesis. So therefore, we're seeing exactly the same result. And we can do that anytime it's a two-tail hypothesis test. We can compare it to the confidence interval. Okay, proportions, same technique, we're just using a different customised formula based on our proportions. So everything we've said today for one-tail, two-tail, that all applies. You're just using your customised proportions formula to get your test statistic. So we've had a few examples. I know I've sped up a bit towards the end. Have a look at this one. You're sending out marketing. The company is claiming to get an 8% response rate. So you've got that to set up the null. You do a survey of 500, get 25 responses. Turn that into your test statistic, set up your decision diagram, and again come up with the conclusion. So have a look at that one. It's the same technique. We're just now using our proportions customised formula. And of course, lucky last, we could have used the p-value for that as well. Now, there'll be lots of chances to practice hypothesis testing. We're pretty much using that technique in different cases until the end of the semester. So work through the tube questions, and I will see you all in a week's time.